Hello. So in this video I want to describe how we in the Flume at Aalborg University for my 8 semesters project are working on the grading of the stones for the scale breakwater. So the Flume looks somewhat like this, and as you can see, this is the homepage from the university. As you can see here, tests are conducted on, for example, scaled breakwaters. And these stones that you can see here, and the filter layer, and also the core, can, if necessary, be mixed to create something that is more coherent with theoretical values. And that is done because of, I think it's called EN3383. So it's this one here. What is it in English? Vandbygningssten. So it's about stones used for offshore engineering, and used typically something that is used is the rock manual chapter 3, which is about exactly this, the stones that are used inside of offshore engineering. So if we go a little bit down, a little bit up again, to around these pages up here, we can see a lot about those different stones used for like harbor construction, offshore construction, berm breakwaters, different kind of stuff. And here they talk about the EN1338 system for standardization of gradings. And this is done because in general producers produce due to these standards, so that we as an engineer can buy what we want. So now I had this problem inside of my scaling, that I was using these stones here in the 6 to 10 tons class. So some heavy stones, some armor stones. It's because in the scale version of my breakwater, the core and the filter layer will use some of the smallest stones at the university lab, and no different stones are available. So I used these stones here. Yes. And as you can see, they typically will spread somewhat in this regard. And also if we go further down below, you can see that we typically will set up some boundaries, and inside of that, this ideal Rosin-Ramler curve will lie. It's the gray line here. And so this is what I've done today. So if we look into the project here, we can see that opening the rock grading Excel arc or Excel sheet. So the homepage is not fully onto that. Yes. Perfect. I will just adjust the size of the window so it's here. Yeah. So if we look at the first one, we can see some different stuff. Yes, I did this in the morning, so be aware of that when I'm talking about what is done here. So what you can see here are the values given by the standard for the limits of where inside the 6 to 10 tons grading of the stones this idealized Rosin-Ramler curve should lie. As you can see down here, it's at 5% it's 4,000 kilograms, at 10% it's 6,000 kilograms, at 50% it's 7,680 kilograms, and this is our lower boundary, and then our upper boundary is up here, where we have at 97% 15 tons, and down below we have 10,000 tons for 70%, so yeah. And here we have 50% for 8,710 tons. And then this is like with kilograms and percentages, but typically in this field of engineering, we use something called the stability number. So the stability number is calculated using a formula that looks like this, where we have H0, I think it's called, is equal to Hs, which is our significant wave height, over delta. Delta is a factor that is used for accounting for the different for the difference in the density. So it's called something like the buoyancy. I don't have the word right now. Yes. So this delta is then multiplied with another value, and this value is. Let me just look here. I know. Yeah, and this value is dn, and dn is our nominal stone length. So yeah, so this is the formula that we will use to find the stability number. And as you can see here, the graph will turn in the other direction, and that is because the larger the stones are, here in the top, the lower the stability number becomes. Meaning that the lower the stability number is, the more stable our breakwater actually is. Yeah, something else that would be interesting to look at is if we look at the lower boundary here, we can see that it's very it's more small, it's more narrow right down below here, where we have lower values, and at the upper values we are okay with having larger values. We can see the same down here. Having larger stones, there's a lot more acceptance for larger stones than for smaller stones, as we can see here. And this makes somewhat sense, because larger stones will typically be more expensive and better for armoring for large waves. Yes. So then we get into this part here, which is a lot more complicated than this. This is more general. So looking at this, we can see that we have different kinds of stones in the laboratory. We have orange stones, yellow stones, green stones, and a lot of different other colors. But these are those that apply to our problem. As we can see, when we made the breakwater and scaled it, the stone size that we calculated for, or the stone weight that we calculated for our stones, was scaled down to 140.29 grams. So the yellow stones are very fitting to that, actually also to the size that we want to see. But this is not realistic that we have so well-fitting stone sizes. So we want to make a blend of some stones. And as you can see here, we have here the upper boundary and the lower boundary, and then we have the Rosin-Ramler curve that we also saw on the other sheet. And then we have some orange stones, equivalent to these orange stones. And we have some yellow stones, equivalent to these yellow stones, and we have some green stones, equivalent to these green stones. Yeah. So what is then done? So yeah, don't consider these lines. They are just trash. I haven't deleted them yet. I should do that. Yeah, so we have taken 100 stones of the orange, of the yellow, and of the green stones out, and know their weight. And we know their weight, let's say that. And then we have the percentages from 0 through 100 down here at the left side. So yeah, and then we have ordered those by weight. Exactly. So what is then done? Then is the mixing already starting. So we have some orange, some yellow, and some green, and we want to mix them so that they are a good mix and a good fit for that curve, somewhat good fit. So I choose so put just some example values here: 0.33, 0.6, and 0.066. So that meaning if you needed 1 ton of your armor stone for the flume, or 100 kilos for the flume is more realistic, then it means like we are using 33.3 kilogram, 60 kilogram, and 6.6 kilogram from the green stones. So this is how it is, and then we mix them so that we get the realistic grading of our armor stone. Yes, and then what we done over here is we will use these grams, this weight, and then we will calculate size of those stones, and for that we are using another formula, and this formula looks like that, where we have the stone size over the weight, the stone mass over the density to the power of 1/3. I think that is how we did it, right? I will just check. So this is the mass over B19. B19 is right here. B19 is orange, so the density of the orange stones. Yes. So this is how we calculate the length of the stones, and you can see here it's 3.1 centimeters, 3.2 centimeters. Yeah, and this is so we get a more accurate sizing of those stones, and that the graphs looks more continuous because it's just 100 stones. And from that we can calculate the HO for that stone, and this is done like I showed before. And adjusting those gradings here, we then get this. The formulas used to get the percentage is this. We use 1% times 0.33, go all the way down here, so we are down at 33.3%. And over here, we then add, do exactly the same, like 1% times 0.6, so we add 0.6%, and then we add these 33.3%. And at last we should get here 99.9. That's because I didn't use an overly amount of decimals over here. Yeah, so this is how the grading is done of the different stones for the armor layer and the flume. Thank you for watching. I hope you find it interesting, and see you in the next one.